Dr. Ranjani Parthasarathy is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science, series of lectures on computer architecture. So we have been looking at the various functional units that we have in the processor. So we are looking at arithmetic units, and in terms of arithmetic units we have already seen what is there for a simple adder subtractor kind of a circuit. So what we have seen with respect to adders and subtractors is we have looked at what we call as ripple carry adders, which are kind of slow adders. So what we are going to take a look at today will be how we can build faster adders, and then we will go on to how multiplication can be done. How do we do fast addition? Okay, that is what we need to look at. So remember that in our basic full adder that we have, right, the full adder, remember, has got 3 inputs xi, yi and a carry input ci, and it generates 2 outputs si and ci plus 1. So the sum bit that we have, the sum output, is basically the exclusive OR of x, y and the carry inputs, and ci plus 1 can be written as xi yi plus xi ci plus yi ci, okay, and 3 AND gates which are OR together. So this is our ci plus 1, and we saw that in a ripple carry adder every full adder will generate this, and this carry out will go as the input to the next stage of the carry, and therefore we have to wait until the carry goes through to the last full adder before the output can be obtained. So now what we are looking at is, can I look at it differently so that I am able to come up with a fast addition. So that is the idea that we are trying to take a look at. Let us look at this equation that we have here. The ci plus 1 we can see is xi yi plus xi ci plus yi ci. Let me just rewrite it as the following. Ci plus 1 I write it as xi yi, but wherever I have this carry here, right, let me just group those two terms together and write it as xi plus yi into ci. So what am I achieving by doing this? I am basically trying to separate out the terms where the effect of the carry is present from the terms which do not have the effect of the carry. So therefore now I can write the ci plus 1 as, I will call it as gi plus pi into ci. Now what is this gi? Gi is nothing but this xi yi, and this pi is xi plus yi. So I am rewriting the same equation as xi yi plus xi plus yi into ci. I am calling this as my g function gi, and I am calling this as the p function or the pi. The reason why we call it as g and p, I will just come to that shortly. G basically stands for what we call as a generate function, and P stands for a propagate function. Now what do I mean by this? That is, at any given position, when will a carry be generated? So remember, when you are adding 2 bits x and y, if the 2 bits happen to be 1 and 1, then I know that a carry will be generated by that particular bit position. If one bit is a 0 and the other is a 1, or if both are zeros, then definitely that addition is not going to generate any carry. But if both the inputs are 1s, that is xi dot yi equal to 1, then it will generate a carry. A particular position will generate a carry if it does that. Another thing is, when will that particular bit position propagate a carry? What do you mean by propagate a carry? That is, a carry is coming in as input from the previous stage, and that needs to be passed on to the next stage. When will that happen? That will happen when either xi or yi is equal to a 1. Okay. So we call this xi plus yi as a propagate function. So what we are essentially trying to do here is trying to identify when is a carry generated at a particular bit position, and also identify when that a carry which is coming in from a previous position is actually propagated to the next stage. Okay. So which is why we are writing our carry, the ci plus 1 output, as either it is generated at that particular bit position gi, or it is propagated, or the previous ci which is coming in from the previous stage is propagated to this position. So there are 2 cases when a carry will be generated. One is that particular bit position itself generates a carry, or that is not generating a carry, but a carry coming in from the previous position is being passed on as the carry over here. So then we call that as the carry being propagated, otherwise we call it as a carry being generated. So ci plus 1 therefore can be written as a generate function plus a propagate function into ci. So now once I have done this, it now becomes easy for me to rearrange these things. So if you look at this Pi and Gi, what we need to note over here is that both this Pi and Gi are dependent only on the values of x and y, they are not dependent on C. So if I am able to separate it out like this, I may be able to see if I can generate all these G's and P's using the x and y's alone, and then use the carries in order to, and then see how I can use that to actually propagate my carries around. So let us see how that will be done. Okay, so let us look at it stage by stage. Ci plus 1 we know now is Gi plus Pi into Ci, this is what we saw just now. You can see that the Ci plus 1 is dependent on Ci. Now what would Ci be similarly? Ci will be dependent on Gi minus 1, Pi minus 1 and Ci minus 1, right. So Ci therefore will be equal to Gi minus 1 plus Pi minus 1 into Ci minus 1. All we are doing is replacing I by I minus 1 because this corresponds to the previous stage input. So now this Ci value can be substituted into the first equation. So what will I get here? Ci plus 1 equal to Gi plus Pi into, now instead of the Ci I am going to bring in this entire equation here. So Gi minus 1 plus Pi minus 1 into Ci minus 1. Okay, so this is what I got. Now look at what we can do further here. Now this Ci minus 1 now can be further replaced by Gi minus 2 and Pi minus 2 into Ci minus 2. So if you continue in the same manner, your Ci plus 1 now will be Gi plus Pi into Gi minus 1 plus Pi minus 1 into, now the Ci minus 1 we are replacing with Gi minus 2 plus Pi minus 2 into Ci minus 2. So you can get the idea of what we are trying to do. So now what will we do now? We can try to now again continue, replace the Ci minus 2 with the corresponding Gi minus 3, Pi minus 3 and Ci minus 3. If you keep doing this until we hit the last digit, which is our C naught, what is it we will finally end up with? We will finally end up with the last digit as P1 into, right, Pi minus 1 into, here let us say this is your P1, P1 into G0 plus P0 into C0. So if you rewrite the whole thing, look at what we are getting here. You will get it as Ci plus 1 will be equal to Gi plus Pi into Gi minus 1, this term here, plus, now for this term it will be Pi into Pi minus 1 into Gi minus 2, plus expanding these things further like this. Let us look at this third term alone here, Pi into Pi minus 1 into Pi minus 2 into Ci minus 2, that will be the next term. So now if I expand the Ci minus 2, it will take me to the next term, right. So if I do that continuously until I come to the end, so what will be my last but one term? My last but one term will have, starting from Pi here, Pi into Pi minus 1 into Pi minus 2 into all the way up to P1 into G naught, right, this G naught, plus this last term here, that will be Pi into Pi minus 1 into Pi minus 2 into etc. into all the way up to P naught into C naught. Now remember, we are not going to go further than C naught because C naught is our basic input that is coming in. So I can see that every Ci that I have, every Ci plus 1 that I have can be written as a function of the P's, the G's and this C naught. Okay. So you can see what we have done by rewriting this equation like this. What we have actually tried to do is, now remember the P's and G's are only dependent on the X's and the Y's. So once I have my P's and G's ready, which can come as soon as I get my X and Y, and I have my C naught, I can directly generate all the C's that we are talking about. And once I have all the Ci's generated, right, then we know that the complete sum that I have can be obtained as Xi exclusive OR with Yi exclusive OR with Ci. So remember, we had to wait in a ripple carry adder for the carry to propagate, right, because the first calculation has to be done, you get the carry out of that, that has to go as the input to the next full adder. Now we are avoiding that and saying that I will generate all the carry inputs from my P's and G's. Once I have done that, then directly I can calculate my S, the sums that I have. Okay. So what we are therefore saying is all the carries can be generated 3 gate delays after X, Y and C naught are applied. How do you say 3 gate delays? Basically all we are saying is we need to do this addition here, right. These AND gates have to be there, AND gates have to be given the inputs and then the output of those have to be put through an OR gate, okay, and they have to be combined, therefore it will take about 2 gate delays. Now to get this P's and G's, I have 1 gate delay. 1 gate delay for generating the Pi and Gi, right. Remember Pi and Gi are very simple, Pi is just Xi plus Y, just an OR gate, Gi is just an AND gate. So I have to get my P's and G's, that takes up 1 gate delay and then I require 2 gate delays for this AND OR circuitry that we have. Okay. So once I have this, within 3 gate delays all my C's can be completed. So once I have all the C's computed, Now all the sums can be obtained 1 gate delay after that. So whatever be the value of n that I have, okay, an n bit addition will require only 4 gate delays, 3 gate delays to produce the various C's and then 1 gate delay after that to produce the S. So this is called as a carry look ahead adder. Now why do we call it as a look ahead adder? Because we are looking ahead to see what will be the various carries generated by just looking at the values of x and y. So you look ahead, find out what the carries will be and based on that obtain the carries and use those carries to actually finally compute your sum. Okay. You can see that now this definitely is a much faster adder, just 4 gate delays independent of the value of n. So when any n bit addition we say can be done in 4 gate delays. So definitely much faster than a serial adder and much faster than a ripple carry adder as well. So the basic circuitry for this will look like this. So we have the different x's and y's going in as input. They are given to the AND gate and the OR gate respectively to produce your generate function and the propagate function G0, P0, so G1, P1 and so on. So you can see that there is an AND gate and OR gate over here. Now these G0, P0, G1, P1 etc. are given as inputs to that carry look ahead circuitry as we call it. Now which will use these values and the carry in C0 to calculate the various C's. Okay. So all your C's come out over here. Once you have got all your C's, then it is only a question of generating the S's by using the corresponding x, y and the corresponding C, XORing them and then getting your S. So what is shown in this circuit is just the carry generation circuitry. Once you have the carries, you just have to XOR it with x and y in order to produce the sums. So this is our carry look ahead adder that we have. We said it can be done in 4 gate delays, but is that really true? Can all these additions be actually done in 4 gate delays? There is one assumption that we are doing there to say that it can be done actually in 4 gate delays. What we are assuming is that even if I have to AND say 32 terms, I am assuming that the 32 bit AND can be done as one single AND gate, just with one AND gate, which means I am assuming that what we call as a fan in, right, number of inputs coming into a gate can be anything. There is no restriction on the number of inputs that can come into a gate. But practically we will find that that is really not the case. So you will normally have restrictions on the number of inputs that can be given to a gate. So when we do that, actually find that when you have these large additions that need to be done, when you look at 32 bit adder for instance, we require 32 input gates. So then that could become a problem because you won't be able to do 32 bit AND or OR in one step, but you may have to do it in multiple steps. So that is one problem that we need to consider. But if you had an AND gate and an OR gate with the fan in of n plus 1 for an n bit adder, then it would be possible for you to get it within the 4 gate delays that we are talking about. But when we look at greater than 4 bits, so there is another thing that we could do, which is that we could combine these 4 bit adders, okay, that is you can split it up into 4 bit blocks and use these 4 bit blocks, concatenate them together to form bigger blocks. That is another possibility that we have. So we will take a short break now and then come back and look at how this blocking of carry look ahead adder can be done. Welcome back after the break. So we were just looking at how we can build large adders, and we saw that the carry look ahead adder is one very fast adder that can be built, and we are also looking at the problem that we have when you have large numbers, because we need gates with large fan in values, that is large number of inputs have to come into the gate. So I said we can look at how larger blocks can be constructed using smaller 4 bit blocks. So let us see how that can be done. So to see that, for a 4 bit block, your C4 is going to depend on G3 plus P3 into G2 plus P3 into P2 into G1 plus P3 into P2 into P1 into G0 plus P3, P2, P1, P0 into C0. Now remember, our P's are our propagate functions and the G's are the generate functions. Okay. So now again I am going to rewrite this as P0 of I, okay, where this I here will denote the blocked carry look ahead, the block number as such. Okay. So I am going to call it as P0 of I as P3, P2, P1, P0. There is this entire thing right here that I am going to call it as P0 of I. And G0 of I will say is the generate function coming out of this 4 bit block. So that I will write it as G3 plus P3 G2 plus P3 P2 G1 plus P3 P2 P1 G0. That is, I am looking at it as this whole thing becomes now my G0 of I, and this block becomes my P0 of I. Okay, P3 P2 P1 P0. So now you can look at your C4 as G naught of I, right, this whole term here, plus P naught of I into C naught. Okay. So, this whole block can be treated as one equation. So, look at this whole thing, that when I say P naught of I, G naught of I can essentially treat it as if it is one single digit. So, looking at it as a digit or as a block, I can now extend this to say that if I want to generate up to a 16-bit adder, it can be done using 4 4-bit adders and by cascading them. Okay. So, in which case what will my C16 look like? It will be the concatenation of these big blocks here, the big P's and G's. Okay. So, it will be G3 of I, G3I, remember that I superscript is there in order to indicate that it is for a blocks generate function. G3 of I plus P3I G2I plus P3I P2I G1I plus P3I P2I P1I G naught I plus P3I P2I P1I P naught I and then C naught. Okay. So, this is what we have as the final function that we have for the C16. You can see how this would basically therefore look like. So, what we have therefore is the 4-bit adders, right, these are independent 4-bit adders. Suppose I want to generate a block 16-bit adder. So, 4-bit adders, 4 individual 4-bit adders, from these I will generate the sums S0 to S3, S4 to S7, S8 to S11, S12 to S15. And what about the carries that I need for that? The propagate and generate functions, the P naught I, G naught I will come as input to this. Similarly, P1I, G1I will come as input to this. Similarly, P2s and G2s will come from here, P3, G3 will come from here. So, once I get these, you use this carry look ahead logic, the one that we saw just now, this big equation that we talk about. So, we use this to generate the different carries. What are the carries that need to come into these blocks? C naught is already there as input here, and then C4 will have to come in as input here, C8 will have to come in as input here, and C12 will have to come as input here. Once that is done, you will generate your actual outputs. So, you can see that the problem of the fan-in that we have can be overcome if we go in for this kind of a block based approach. So, take smaller blocks of 4-bit adders and use them to construct larger adders, and in fact you can go on extending the same thing. Okay. So, with that way you will be increasing the gate delays slightly, definitely not to the extent of a ripple carry adder, but you will also be able to manage it with the limited number of inputs to a gate. So, with the limited fan-in you will still be able to handle this. Okay. So, this is what we have with respect to adders. So, with respect to adders, therefore, we have looked at 3 types of adders, the sequential or serial adder as we call it, and then we have looked at a ripple carry adder, then we looked at some fast adders. Let us look at multipliers. Now, multiplier is a very simple function that we all are familiar with. Now, remember your normal pencil paper based multiplication that we do, and let us see how that is done for binary numbers. We will start with unsigned numbers. So, let us say I have 2 numbers 1101 and 1011 that need to be multiplied. So, what do? So, we all know that, right? We take each bit of the multiplier, let us say we will call this number as the multiplicand, this is the multiplier. Now, I take each bit of the multiplier, I see whether it is a 1 or a 0, right? If it is 1, I multiply it with the multiplicand, write it down here. If it is a 0, you multiply it with that and write it down. Only thing is, when we are dealing with binary numbers, addition by 1 is basically copying down that same value here, multiplying by 0 is putting zeros in that place. Okay. So, look at what we will have here. The first step therefore will be 1101, because this bit is a 1, next bit is a 1, therefore again you will have 1101, next bit is a 0, so you will have 0000, next is a 1, so 1101. Only thing is, remember we will shift the positions here and then we add all these different what we call as partial products that are generated. Okay, we refer to these as partial products. The partial products will all be then added together to get your final product. Now, this multiplication we are all familiar with. So, how do I construct a circuit to do this? Now, what is it that we are doing here? Look at each step that we have. If you look at each step, what did I do here? I basically multiplied my 1 with each of these numbers. Now, what is multiplication involved? If it is a 1, it is 1 into 1 giving me 1. If it is a 0, 0 into something giving me 0. So, the multiplication of each bit, that is, if I look at a bitwise multiplication, it is nothing but an AND gate. So, you can see that all I need is an AND gate to generate these products, okay, these partial products. That is, if there are 4-bit numbers, I need 4 AND gates to generate these partial products. And then once I have these products generated, I need my adders in order to add these numbers up to come up with the final answer. Okay. So, you can see that it is nothing but the generation of partial products using an AND function and then adding of these partial products. But the only thing we have to remember is when you do the addition, it is a shifted addition that we need to add. Okay. It's a shifted addition that needs to be done. So, let us see how this can be done. Okay. We will first look at unsigned numbers, because signed numbers we will look at a little later. there are two things that we can talk about. In the normal paper pencil method or the method that we talked about over here, we do this addition, right, this partial product addition at the very end. That is, we generate all the partial products and then we do the addition. It is not necessary to do it that way. For instance, you could also, once you generated a partial product and you generate the next partial product, immediately I could add these two, and then I generate this product, I could add these three. Then I have this up to this addition done. Once I generate this partial product, I can add that as well. So if you do that, you may be able to speed up the entire process. So that is one way the actual multiplication is normally done. So we will take a look at how that is done. So the rules that we have basically to implement multiplication are, if the ith bit of the multiplier is 1, you shift the multiplicand and add the shifted multiplicand to the current value of the partial product. Initial partial product value will be 0, okay, and then hand over the partial product to the next stage. What will the next stage do? Again, that will look at the next bit of the multiplier. Based on that, shift the multiplicand and add the multiplicand to this value. This is what we would require. Now let us see how this can be done with the AND gates and the adders that we talked about. One way to do this entire multiplication is using what is called as a combinatorial array multiplier. So let us see what we have in this array multiplier. It is very simple. So what you have is, you have these different blocks here. Now what are these blocks here? These blocks are the fellows who are going to generate an AND of the multipliers and the multiplicands. Now let us understand what these different m's and q's here are. The multiplicand is given as m0, m1, m2, m3. Now this is what the example we are looking at is a 4 by 4 multiplier. So m0, m1, m2, m3 are the multiplicand bits, and q0, q1, q2, q3 are the multiplier bits. Okay. So depending on the multiplier bits and the multiplicand bits, the different partial products have to be generated. Okay. So let us see, we put a block over here. Let us see what will be there within each of these blocks. Okay. If you look at each of those blocks, what we call as a multiplication cell, okay, what we have inside that is this. You have the product that is generated at that particular bit position, that is the ith multiplier bit and the jth multiplicand bit. Now remember, multiplication of these two bits is just the AND of those two bits. So we have an AND gate here in order to generate that particular the multiplication output. Okay. So that value is there, and remember what we need to do. We have now added to the partial product which is coming in from the previous stage, okay, and if there is any carry coming in from the previous stage, that also needs to be added, right, and this will generate an output which will be the outgoing partial product output, and if any carry is to be generated from here, that will go out as the carry from here. So let us just go back here and see what we are talking about here. So within this block I am talking about multiplying m0 and q0, okay, adding any carry which is coming from here, okay, generating my p0 here. If I look at this bit here, what I would be doing is multiplying m1 and q0, and any carry that was coming from here will also be added to that value and passed on as the input to this next partial product generation over here. Okay. So in this stage what will happen is m0 and q1 as the input, okay, remember this coming from here, m0 and q1 as the input. Now these two will be multiplied and added to the partial product coming in from this previous stage, and this will generate a sum and a carry. So if you look at this stage, you will see all the things in action here. If you look at this particular stage, you can see that this basically multiplies m1 and q1, adds this partial product, also adds, the carry coming from here, and also adds the partial product from the previous stage, generates a carry that has to go over here, generates the next partial product output that needs to be stored here. So using these simple cells, okay, which just consists of a full adder and an AND gate, okay, you come up with these small cells, and we connect up these cells in such a manner that you can pass on the inputs, the corresponding inputs to all the cells, and get the output correctly. Okay. So let us just look at how that will work. Okay. Just show you a simple example of how this will work. Okay. So let us say we have the multiplicand inputs as 1101 given over here. Okay. So what is done is this 1101 input is something which will be passed on to all these different cells over here. Okay. So this means, so when this 1101 flowed in over here, it meant that 1101 is an input that is given to each of these blocks that we had here. Okay. So next we have 1011 as the multiplier. Okay. So 1101 is the multiplicand and 1011 is a multiplier. So again similarly this multiplier goes as an input to all the cells that we have here. Okay. So that is something we have. So 1101 and 1011 are the multiplicand and the multiplier that we have. Now look at what is happening at each stage. Okay. So remember this is the first bit that we will take a look at. So this gets various inputs, right? It has a carry input, a previous partial product input which is going to be 0 because there is nothing else coming in at the first stage. So, initial partial product input is 0 and your initial carry input is also 0. The multiplicand bit is 1, multiplier bit is also 1. So, let us see what. So, it will produce a output of 1. You can see what is happening inside that. So, this 1 will be passed on here. Then similarly, this 1, the multiplier bit also will be passed on to the next block, and then inside we have this AND gate and the full adder, right. So, you have 1 coming in as the input to the full adder, and then this one also coming in as the input to, coming in as input to the AND gate. Now, the AND gate will produce an output of 1, okay, and then the initial partial product 0 comes as input to the full adder, and the carry in 0 comes in as input to the full adder again. This produces an output of 1 which is the partial product that will come out, and then it will produce a carry of 0, and this carry will be passed on to the next stage. At the end of this first cell's operation, okay, you will find that these are the values that are generated. So, now what will happen is at this, if you look at this, you have one output that has already been produced. Okay. Now, you can see what is happening with the same kind of operation now will take place at the next stage. Only thing is this cell's operation is complete only after the carry from this is generated. So, that is all that we need to keep in mind. So, look at what is the value that we have here. So, if you look at this stage here, similarly the 0 is passed right through, 1 is passed right through, then to the full adder we have the inputs coming in as 0 is one input, 1 is one, to the AND gate, sorry, to the AND gate 0 is one input, 1 is one input, which gives you a 0 as the output of the AND gate, and then the partial product is 0, carry is 0, gives you an output of 0, and you get a partial product of 0 and output of 0. Okay. So, this is basically what will happen. So, you will see that this kind of a process will take place right through. Once you have done this, so at the end of this process, right, after the carries have propagated right through and after all the partial products have been calculated, you will get your final sum as the output over here. Okay. That is what you, final product as the output over here. So, this is called as a combinational array multiplier. Now, we said it is an array multiplier because it is an array of gates that we have. Okay. The only problem with these array multipliers are that they are that they consume a lot of circuitry as we saw, because you need to have so many AND gates and those full adders. Okay. So, if you look at a 32 cross 32 multiplier, you require 32 adders and 32 AND gates, but it is a fast multiplier in that sense. One way to improve this will be to do it as a repeated addition process, that you can use limited number of adders and try to do it in a repeated process. So, that gives us a different kind of a multiplier. So, we will take a look at that in a subsequent session. Yeah. So, to summarize, what we have looked at today is some aspects of how a fast adder is built. That is, we looked at the carry look ahead adder, and we also saw how larger carry look ahead adders can be built using the concept of blocked addition. Okay. Then we also looked at basics of multiplication and how an array multiplier is built. So, we saw that just using a simple AND gate and full adders, an array multiplier can be built. So, some questions for you to review today's lecture. Question number 1, what is the advantage of a carry look ahead adder? Question number 2, what is the disadvantage of a carry look ahead adder? Question number 3, what are the basic functions used in a multiplier circuit? Question number 4, what would be the time taken by a 4 cross 4 parallel array multiplier? Question number 5, write down the intermediate steps in the following multiplication, 12 into 14. Okay, that is a 4 cross 4 multiplication. Thank you.